Matthew Morrow, who's going to give his, I guess, second lecture on topological Hochschild homology.
Good, yeah, thanks very much. So how's the mic? People hear me okay? Not too much feedback, good sound, getting some nods, that's a good sign, great. So I just wanted to start by giving a quick overview of what we did last time so that you know what you need to remember for today's talk and what you can safely forget. So we had some algebra A over some commutative base ring K, and we associated to that this so-called Hochschild complex. So this was initially some simple chain complex. We wrote down various tensor powers of A. We had maps going down given by explicitly taking alternating sums of multiples of adjacent elements, including the last element by the first element. And then using the fact that each of these tensor powers is equipped with some action by the cyclic group, we wrote down, using a sort of norm map, a map in the other direction, which was called big B, and gave it the structure of what's called a mixed complex or an algebraic S1 complex, essentially simultaneously a chain complex and a cochain complex in a compatible fashion. And we saw various connections then between the homology of this complex and differential forms. There was always a map, and this map was an isomorphism in the smooth case. Next, we wrote down this big old nasty anti-commuting double complex in which the columns are given by copies of the Hochschild complex itself, and to produce the horizontal differentials, we used this B structure of a cochain complex. So the product totalization of this big gadget was what we call the periodic cyclic homology, so that's some complex going infinitely in both directions. If I only totalize some left half plane of it, I get what's called negative cyclic homology, so that then embeds into the totalization of the whole thing. And the totalization of some right half plane copy is what's called cyclic homology. And so I've just lost the last little bit. So under these explicit definitions, I have an exact sequence of these complexes, negative cyclic homology sitting into periodic cyclic homology, and then projecting down onto the cyclic homology. And I wanted to make, again, this point that I finished with last time because it's going to play a role today, that if we happen to plug in a ring for which all of the homologies of the Hochschild complex vanish in odd degree, then we get lots of stuff for free. So that will then tell us that in this spectrum, so that in this, when we start turning the handle on the spectral sequence associated to this double complex, well, on the next page, all of the homologies in all of the columns will be supported in even degree. And so just by looking then at the convergence of the spectral sequence, we'll deduce that also the homologies of HC minus, HP, and HC are also all supported in even degree. We just get that free from the spectral sequence. And so then this norm sequence necessarily has the split into short exact sequences when we look at the homologies. So we get these short exact sequences as follows of the HC minus homology groups sitting inside the HP homology groups, projecting down onto the HC homology groups. And since periodic cyclic homology is periodic, you can read off this bicomplex, I can identify the HP2n with HP0. So these are the 0th and the 2n homology groups of the HP complex. These are going to be the same. And so I can view, in fact, this HC minus 2n group as sitting inside HP0. And in fact, the structure that you get there is that this HP0 becomes a filtered ring, filtered by ideals coming from negative cyclic homology, and the associated graded will look like the difference between one copy of the HC complex and the shifted copy, which is exactly a copy of the column, which is Hochschild homology. So somehow coming from this structure, we just build freely some interesting filtered ring, which is including essentially most of the data of the periodic, the negative cyclic, and the cyclic homology. So I want to start today by somehow finishing the story of classical cyclic homology by presenting what is in some sense the main, let's say, main theorem about smooth algebras. So this is, as I say, this is part of the classical story attributed to various people like Lode-Quillen, Fagan-Segan. I guess surely it's in some paper of Kohn. So it says the following: if A is a smooth, so we'll get back to our smooth case, a smooth K algebra, and we're going to need an extra hypothesis. We'll get rid of this in a second, but for the proof I'm going to give right now, I do need it. I'm going to assume that our base ring contains the rational numbers. You could take it to be a field of characteristic 0. This is generally what happens when you look at the classical papers. Then this so-called norm sequence, I'm going to tell you what all the terms in it look like. So it looks like a big product over all integers of question mark shifted by 2i, where question mark is the following. So let's get the degrees right. I look at the RAM complex for a over k. I truncate it a bit, and then I look at the remaining piece. So let me break down what I want to say here. I have HP of my smooth algebra, and I'm saying this just looks like a product over infinitely many shifts of this term. The HC minus complex looks like a product over infinitely many shifts of this term, and the HC complex looks like a product over infinitely many shifts of this term. And these decompositions happen in a compatible way, as you would expect, looking at this inclusion of a truncated de Rham complex into the de Rham complex. So the moral to take away from it is that the periodic cyclic homology in this case is basically looking like de Rham complexes. So it essentially encodes and doesn't give much more than the theory of de Rham cohomology. And negative cyclic homology, which looks like product of copies of this, is exactly encoding for us the Hodge filtration. That is to say, truncations of the de Rham complex. So this is very easy to prove based on what we already know. So we're just going to write down some explicit map. Since this is the classical story, I'm trying to present everything as explicitly as possible. So let's have some explicit map of chain complexes from the Hochschild complex, it's HH of A over K, to what's going to look like a pretty dumb complex. I put an A, put an omega 1 of A over K, put an omega 2 of A over K, and so on, where I wait for someone to ask a question. What are the maps? There's 0. What else could they be? There's no reasonable maps. Thank you. So it's not the de Rham complex, indeed, because I'm trying to write down a map of chain complexes. How do I do this? I send some symbol A0 tensor through AN, that's sitting in degree n of the Hochschild complex, and I send it to 1 over n factorial, A0 dA1 wedge, yada yada, wedge dAn. So one checks that this is indeed a map of chain complexes. So that is to say, what do I need to check? I need to check that if I apply the boundary in the Hochschild complex, and then I go over to the de Rham side, that I get 0. In fact, one needs to check, but one just does it. It's an explicit calculation. And taking homologies on both sides, so on each homology group Hn, one checks also that this splits the map that we wrote down last time from omega n to HHn. So the homology of this complex on the right are just the omega n's. The homologies on the left are Hochschild homology. So we already have a map from the homology on the right to the homology on the left. And it turns out that this new map that I'm writing down splits that old map. Again, this is just an explicit calculation. Now, I'll tell you what, I'm just going to put a QED box and explain the rest orally. No, there we go. No, really, we're there. So because I'm a smooth algebra, we saw last time that these maps are all isomorphisms. So that tells me that this map delta must in fact be a quasi-isomorphism. It's inducing isomorphisms on all the homology groups. So now if I come over to this double complex here, I can replace up to quasi-isomorphism. No, I should write down one more word. I can replace up to quasi-isomorphism all of the columns which are appearing by this dumb-looking complex, because it's a quasi-isomorphic column. And we've also seen that the B operator which appears is compatible with the de Rham differential that appears on this side. And so this big double complex then just looks like a bunch of copies of de Rham complexes with 0 vertical maps appearing. And so when I totalize, I end up just getting products of copies of de Rham complexes. And that's, as I say, that is essentially the end of the classical theory as I want to present it. And our goal now will be to move on a little bit to the situation in characteristic P. So let's say cyclic homology and all of its variants in characteristic P. And here the essential theorem. So we used, you see, we used in this argument somehow, I needed an n factorial. And this n factorial was just to make sure that we correctly split the anti-symmetrization maps that appeared. But let's now look at some smooth algebra over Fp. Then, let me say informally, so the classical theorem in characteristic 0 is still true, but the filtration is not naturally split. So let me explain in more details what I mean by that. So for example, let me focus on the HP term, and here I've made some statement about the negative theory, the periodic theory, and the cyclic theory, but let me just stick to HP. So for example, this, let me work over FP, this complex of periodic cyclic homology of FP, of this smooth algebra, this has a filtration whose graded pieces are all possible shifts of the de Rham complex. So in this characteristic 0 situation, I was saying that this HP complex decomposed into an infinite product of all shifts of the de Rham complex. And what we lose in characteristic P is just that this happens in a non-split fashion. So I still have some filtration, and each of the pieces looks like a copy of the de Rham complex, but I can't necessarily split my filtration. And I was super confused about whether this was known to be true or not since yesterday when Alex Petrov, who's in my project group, I've explained a super classical proof of how you could prove this and why it should have been known for 40 years, and yet one doesn't really find it in the literature. But I'm convinced that it seems okay. So let me give a classical, there's some classical then forgotten proof involving yoga of double complexes. So what one does, so we have an explicit description of HP as the totalization of this complex, and I can produce some filtrations on this in various ways. So in particular, I can impose the canonical filtration on every column which appears. And that will induce a filtration on the totalization, which you can compute by the fact that we've computed the Hochschild homology groups in terms of differential forms and the B operator in terms of a de Rham differential. And there don't seem to be any convergence issues. I thought there were, but he's convinced me that in fact it's okay. And so we should have known for many years that one picks up, as I say, a non-split version of the classical characteristic 0 filtration. Nevertheless, what I want to explain today is an alternative approach to analyzing periodic cyclic homology in this sort of setup, the advantage of which, so let me make one of these super imprecise statements, analysis of the periodic cyclic homology via perfectish rings. The advantage of this, so why do I bother doing this, is that this will generalize to the topological framework. So next time I'll start discussing topological Hochschild homology, and then we won't be able to write down explicit double complexes representing things. We'll just have some abstract construction of these theories, and there also we'll want some tools to analyze these theories. And so I want to introduce in this slightly nicer context of classical cyclic homology and periodic cyclic homology, where we can at least write down explicitly what's going on, these sorts of tools that we'll really crucially have to use once we pass to the topological theory. So the idea is the following. We're not going to try to study smooth algebras directly. They're too complicated. Somehow computing complexes is hard. The only thing we can really compute in life are abelian groups. So we have to somehow reduce to that case. And we do that by instead, we'll find some technique which will let us replace calculations of smooth algebras to the case of what are called quasi-regular semi-perfect, which for good reason we adopt an abbreviation for. Let's call them QRSP, FP algebras. So these are big, in particular than non-Noetherian in general, except in some very trivial cases. But they're somehow homologically simple. And this homological simplicity of them will simplify what's going on in periodic cyclic homology and allow us to really explicitly calculate. So, that's enough for informal philosophy. Let's have a definition. So what is a quasi-regular semi-perfect ring? So we say that an FP algebra A is quasi-regular semi-perfect. So if there exist some perfect algebra, let's say S, so that means, actually let me call it B, that's maybe going to look better. So that means that every element of B admits a unique p-th root. So the Frobenius endomorphism of B is an automorphism. And that immediately puts us in the non-Noetherian context. Unless B is a field, then this has to be a very big non-Noetherian ring. And secondly, I ask that there exist, let me look at a special case, a regular ideal, I contained inside B. So regular means that I mod I squared is, let's say, finite projective. We could slightly loosen this, but I think we can work with finite projective today, is a finite projective B mod I module, and I think I can finish the definition on this page, such that B mod I is equal to A. So in other words, I ask that spec A, let's think of it like this, I ask that spec A can be regularly embedded, not into a smooth scheme, that's what you very often do, I ask that it can be regularly embedded into a perfect scheme. Because perfect schemes and perfect rings will be the things that we can understand. So I want to be as close to this as possible, so I'm some regularly embedded into a spec of something perfect. Let me make some comments on this regular ideal business. So example of regular ideal. if I'm generated by a regular sequence, then I'm a regular ideal. That's a reasonably classical piece of homological algebra. In fact, this hypothesis of being a regular ideal can be slightly weakened. You don't need I mod I squared to be finite projective. You could ask it to only be flat. But this is not really going to play any role today. In fact, you should imagine that you are just given by some perfect FP algebra modulo some regular sequence. And that, I mean, as we'll see, is in fact the case that naturally arises. So here are some examples of such things. So the prototypical example, let's form the first non-trivial perfect FP algebra. I can look at FPT, and I can adjoin all p power roots of t. And then I can mod this out by the ideal generated by t. So I've taken some big perfect ring, and I mod it out by a single non-zero divisor. So how on earth can we possibly study this smooth algebra that we want to look at in terms of such enormous ugly rings? It turns out they naturally appear. So if R is a smooth FP algebra, well, first I can perfectify it as follows. So R sub perf, this is what I get when I take the colimit over iterations of x goes to x to the p on R. So it's the initial perfect FP algebra which is receiving a map from R. I just adjoin in a nice way all p power roots of all elements. Well, and then what sort of terms would we see in the Hochschild complex? In fact, we won't be so interested in these because of the Hochschild complex, but they're the same. Well, they're the same terms, so let me write them down. Let me form a bunch of tensor products of this perfect R algebra over R. These I claim, well, so this thing, there's some number n, so this thing is quasi-regular, semi-perfect. So here's an example, which I hope will convince you that it's true. Now what's our favorite smooth FP algebra? Let's just take FPT, and I perfectify it, tensor it over FPT with another copy of FPT perfectified. So I'm considering this type of construction, in the case of R just being FPT and only having two copies. But this is really the prototypical case. I mean, dealing with more tensor products is not an issue. And in general, whatever your smooth algebra is, then it's going to be a tau over a polynomial algebra in some number of variables. Dealing with the tau piece is okay, and so you just need to rewrite the argument that I'm about to do in the case of more polynomial variables. So how does this thing look? Well, when I perfectify these two terms, I get an FPT to the 1 over p infinity. I tensor it over FPT. I have another FPT to the 1 over p infinity. And overall, well, that looks like a perfect polynomial algebra in two variables. And I have a single relation that T1 is the same as T2. But T1 to the 1 over p is not necessarily the same as T2 to the 1 over p. So I've adjoined two different compatible sequences of p power roots to my polynomial variable. And indeed on the top here I have some perfect FP algebra, and I'm just modding out by a single non-zero divisor. So we see that starting with a smooth FP algebra, that's what we want to study, we can build, using this sort of tensor power construction, lots and lots of quasi-regular semi-perfect rings, which I'm telling you will turn out to be homologically simple and easy to analyze. So how does this argument actually go, and how can we analyze all of these gadgets to get back to the smooth algebra? So let me present this as a general technique, because we'll apply it today for things like cyclic and periodic cyclic homology, but then probably not tomorrow, but the day after, we'll instead plug in things like topological cyclic homology. So let's say here's a technique to go from quasi-regular semi-perfect rings back down to smooth, which says, I keep trying to emphasize, these look like very different worlds. These are some massive non-Noetherian rings containing lots and lots of p-power roots, very far from smooth algebras. So the point is that all of our homology theories, let's call a general such thing F. So I'm imagining like Hochschild homology of some algebra over Fp, or cyclic homology of some algebra over Fp, or the negative cyclic homology, or the periodic cyclic homology. And so I think of these, this is some process which takes in an Fp algebra and spits out some complex of Fp vector spaces. All of the theories that we'll be interested in satisfy what's called flat descent. And what that means concretely is that if I've got some, let's say S to S prime is a faithfully flat map of Fp algebras, then, so I can do the following. I can look at the value of my cohomology theory on S, and I compare it to the following. I'm going to totalize something. I'm going to totalize the check construction associated to this cover. So I look first at my cohomology for S prime. Then I look at the cohomology for two copies of S prime tensor together over S, and so on. Then I would have three copies. And so this forms for me, so F is some complex, so I get some cosimplicial complex, I can totalize it, and flat descent means that the value of my cohomology theory downstairs can be computed by the value of the cohomology theory upstairs and looking at all of the associated terms in the check cover. And as I say, that turns out to be true for all of these theories that we're interested in, like Hochschild homology, cyclic homology, periodic cyclic homology, also all of the topological variants. Yes?
Is that an isomorphism of complexes or quasi-isomorphism?
No, that's a quasi-isomorphism. That's a quasi-isomorphism. At some point, we're going to end up slowly becoming more and more derived. This is just a statement about behavior in the derived category. Yeah, thank you. So for example, and here somehow comes the key, so if R is smooth over Fp, then we have a preferred faithfully flat cover. This map from R to its perfection. So why is that? So when you add p-th roots in characteristic P, these are radical extensions. They don't change the spec of your ring. And that will ensure that if we get a flat map, we get a faithfully flat map, because it will automatically be surjective on spec. And for flatness, well, again, we argue that because R is smooth, it's going to more or less look like a polynomial algebra. And in the case of a polynomial algebra, you see very directly that when you extract p-th roots of all the variables, this is a flat operation. It's even a free operation in that case. And there, actually, one crucially does use the smoothness hypothesis. And it's indeed it's a classical theorem in commutative algebra due to Kuntz that this extraction of applying, that this process of applying the Frobenius will be flat if and only if you are smooth. So one really heavily takes advantage of the smoothness condition here. And so the conclusion, putting everything together, is that if I'm trying to compute, trying to control the behavior of some cohomology theory on a smooth algebra, I can instead do the following. I can look at the value of my theory on its perfection. Sorry, these are long expressions, and I find I don't quite have enough space on the paper. Maybe I'll try again. So we put that up there. Start over here. I'm trying to understand the value of my cohomology theory on R. I get that as follows. I look at the value on R perf. Then I look at the value on R perf tensor over R perf. Then I'd have 3 copies and so on and so forth. So here R is some smooth algebra that we want to understand, and by this argument we had a moment ago, we know that all of these tensor powers of R perfs over R, these are quasi-regular semi-perfect rings. And so I get some way of determining, I get this equivalence that the cohomology theory on R is completely determined by the behavior of the cohomology theory on these quasi-regular semi-perfect rings. And so whatever we want to understand, and this is true in some functorial fashion, because the process of extracting, of passing from a smooth algebra to its perfection is functorial and well behaved. And so whatever we want to understand about our cohomology theory on something smooth, we can read off the data from its behavior on quasi-regular semi-perfect rings. And there, as I say, we'll actually be able to explicitly calculate what's going on. Of course, we now need to understand the right-hand side, and that's the next thing I want to discuss. So we must understand. So let's see, which things do we want to do? Let's say, well, ideally we'd like to do all of them. We'd like to understand the negative cyclic homology, the periodic cyclic homology, and the cyclic homology of any quasi-regular semi-perfect FP algebra. We don't really need any, I gave an abstract definition of this sort of ring. We only really need to understand the sorts that actually appear in this type of construction, but it doesn't change anything to analyze it in greater generality. So I take A to be some quasi-regular semi-perfect. And step 1, the first thing one checks is that the odd Hochschild homologies of this type of algebra all vanish, which is why I've been laboring this point now twice, that in the case in which the odd Hochschild homologies vanish, somehow all the information that we want is just encoded in the data of an HP0. So everything that we want to say about all these gadgets appearing on the right-hand side will just be contained in the data of some single filtered ring. And that's ultimately what we'll have to analyze to finally get all the information about the left side. Okay, so the odd ones vanish. Let me also say something about how this looks in even degree and how one extracts this sort of information. So these vanish, and okay, HH0, let me stop writing the A over FP, it takes up too much space. So HH0, we already know that's just a copy of the ring that we did as a general calculation last time. HH2 will look like I mod I squared, where we recall that we write our quasi-regular semi-perfect ring as something perfect modulo some regular sequence. And then the HH2 will look like the co-normal of this regular sequence, that is to say I mod I squared. And more generally, HH2n will look like the nth divided power of I mod I squared. I think I wanted to say a word about this divided power business. Something's gone wrong here, hasn't it? That should be over there. That should be there. Except it shouldn't be anymore because I need the space. So as a module, I mean, this divided power as a module is in fact, since this is a free module, it's just looking like the nth symmetric power of I mod I squared. But multiplication is twisted by, so let me write this down and then explain a bit. Let me say n factorial n plus m factorial. Oh, factorials are hard. Let me cheat. Here's something I prepared earlier. N plus m factorial over n factorial m factorial. Okay, what do I mean by this? Let me write down the final conclusion. Okay, let me now say some words to explain what's going on. So in fact, if I take any A module M, let's suppose it's flat though. In fact, let's suppose it's free. Well, it's finite projective, it might as well be free. Then you can define this divided power polynomial algebra on the module. So let's suppose we've picked some generators of the module for simplicity, and then you form this divided power polynomial algebra. So it looks a priori, if you just think of it as an A module, it just looks like a normal polynomial algebra. But then you twist the multiplication so that if you're multiplying something in degree n by some polynomial in degree m, you throw in an extra factor of n plus m factorial over n factorial m factorial, so that you can think of your polynomial variable in degree n as in fact being x to the n over n factorial. So you've got this polynomial algebra in which you're formally adding these so-called divided powers of all the variables. And that is how the Hochschild homology groups in odd degree of this sort of algebra will look. And this follows from some classical fact. Sorry. Well, it follows from this description of HH2. Yes. So the answer is yes. So here's the key word. Somehow I was.
What was the question?
So the question is it obvious that I mod I squared does not depend on the way in which we've chosen to present A as a perfect ring modulo a regular sequence? And the answer is not quite no. So let me write down the key word. So the key word is okay, it's two words. The keywords are cotangent complex. Well, I don't know if complex is the key. Okay. So the cotangent complex. So if you have any, let's say, FP algebra A, that's what we've got here, then one associates to it this so-called cotangent complex. This is a theory developed by Illuzy, Quillen, and André in the 70s. So this is a complex depending only on A, which governs the deformation theory of A. In the case in which A is smooth, it doesn't contain very much information, and it in fact just looks like omega 1 of your ring. But generally it contains some higher order homological information. Now one sense in which these quasi-regular semi-perfect rings are homologically simple is the fact that so I've built them first by taking a perfect algebra, and perfect algebras actually have trivial deformation theory. More precisely, their cotangent complex is 0. So they both sort of look smooth in that the only contribution to their cotangent complex is coming from omega 1, but even better, this omega 1 is 0. Because if you have a perfect ring, it can't have any differential forms. As soon as you can write f equals g to the p, then d of f equals 0. Because it equals pg to the p minus 1 dg. So the cotangent complex and all the deformation theory for perfect rings is trivial. And so the deformation theory and the cotangent complex of something like A, all of the data is just coming from modding out this regular sequence. And there are classical results that when you mod out by a regular sequence, what appears in the cotangent complex are copies of divided powers. And so firstly, you can give an intrinsic characterization of this I mod I squared by writing it down as being the cotangent complex of A over Fp. So secondly, as we've seen, we have various relations between the Hochschild complex and the Hochschild homology groups and differential forms. This can be jazzed up to relationship between the Hochschild complex and this cotangent complex. That's somehow the right replacement for differential forms when I'm not necessarily smooth. And you can then read off this type of relation, these descriptions of the homology groups, using classical calculations of the cotangent complex. And so once we know this general property that the odd Hochschild homology groups are vanishing for this type of ring, then by this general principle I've been mentioning several times, we deduce that most of the information in these cohomology theories is captured entirely in this filtered ring HP0. So let's say this is a filtered ring with associated graded given by this divided power algebra construction on I mod I squared. By this general nonsense that I mentioned at the beginning, that whenever you're vanishing an odd degree, you get such a result. You can just read it off the spectral sequence. And so the key point then, and then everything else will just be formal, is whether one can identify this graded ring. Excuse me, this filtered ring. Because if you can identify this, then you chase back, we've got a description of these theories like HP of R in terms of HP of this type of algebra. And if you chase through the definitions, as long as you've got some good enough understanding of this filtered ring, which also, I emphasize again, will give you all the information about the negative cyclic homology and the cyclic homology, because that's encoded in the data of the filtration. As long as you can identify that, you get everything essentially for free. So what is it? Well, I'll just tell you the answer. Essentially, there's only two options. I should insert a word completed. Again, let me write it down and then explain orally what's going on. So I've written my algebra A as B mod I. So I've got this ideal I sitting inside B. And there's a classical structure that you can do coming from the theory of crystalline cohomology and de Rham cohomology. I can add to the ring B in some formal way everything that looks like f to the n over n factorial as I run over all f's in the ideal and all n's. So this, of course, doesn't really make sense, especially since we're in characteristic p. You can't divide by p factorial, but the theory of divided powers gives you a formal way of making this happen. In a similar way to that a moment ago, we could looked at some sort of divided power polynomial algebra just by rescaling multiplication to make it so. And it's, again, classically known in the theory of divided power, in the theory of the algebra of divided powers, that if you add divided powers along some ideal generated by a regular sequence, then the associated graded ring will look the same as this. And so one knows classically that the divided power envelope and this HP0 will have the same, there'll be complete filtered rings with the same associated graded. And the hard work is to check that they're actually isomorphic on the nose, not only the associated graded. And for the moment, I consider the proof of the construction of this isomorphism to be a little bit unsatisfactory. We have several ways of proving it, but I've set as a project, in fact, a sort of hands-on way using the fact that periodic cyclic homology of group rings is closely related to group homology, which typically sees divided powers. So by using this type of argument, one should be able to construct lots of divided powers sitting in HP0 of these types of rings, and then using the universal property of the divided power envelope, should be able to construct a map into it and explicitly check that it's an isomorphism. But so far, this sort of hands-on local proof has not yet been carried out, but I'm reasonably convinced that it should be able to be done. And so the conclusion then so our goal was to say something about the periodic cyclic homology of a smooth algebra over Fp and the conclusion is that this is built from copies, that's not good English, it's built from copies of, or more precisely, filtered by various totalizations of the following. So I return to my HP0 of R perf over Fp, HP0 of R perf tensor R perf over Fp, and so on. So we saw that the periodic cyclic homology of R itself, so what I've written, okay, the periodic cyclic homology of R was in fact determined by the totalization, not of the homologies of these terms, but really of the periodic cyclic homology complexes of all of these terms. But each of those, is strongly controlled by what's happening to the individual homology groups. And these terms, these are all some zeroth periodic cyclic homology groups of various quasi-regular semi-perfect rings, which we know are all controlled by divided powers. And so the final step in finally understanding what's going on in the periodic cyclic homology of this sort of smooth thing is that these divided power envelopes also show up, I'm being very imprecise here to finish, in, let's say, theory of derived de Rham cohomology. Particularly due to work of Bhargav Bhatt. So you can identify these divided power envelopes that are appearing, which are describing HP0, in terms of certain derived de Rham cohomology groups of all of these quasi-regular semi-perfect rings. And it then follows formally from another descent argument that the totalization of this complex is exactly producing for you a copy of the de Rham complex of R over Fp. And that's the essential way in which copies of the de Rham complex of this smooth algebra show up by passage through these quasi-regular semi-perfect rings where you compute everything on the nose as abelian groups or as filtered rings. So next time I'm going to discuss topological cyclic homology. And the goal after that will then be to try to run through this same sort of argument in those cases and describe topological periodic cyclic homology of these types of quasi-regular semi-perfect or even quasi-regular semi-perfectoid rings, where new and more interesting things than de Rham cohomology will show up. So I finished there. Thank you very much.
All right, questions?
Are there any obstructions to sheafifying all of this, like replacing R with a no?
No, no.
It's good.
Does the base have to be FP? Could it be
No.
a different characteristic P thing?
It could be any, I mean, to make things go really, really smoothly, you could take any perfect field of characteristic P. With a little bit more work, you could take any not too singular ring of characteristic P.
Thanks.
How do you show that the HH odd of quasi-regular semi-perfectoid or semi-perfect rings are zero?
So as I say, you read this off the cotangent complex. So you have a spectral sequence describing Hochschild homology in terms of the homology of all wedge powers of the cotangent complex. So this comes by the calculation in the smooth case that, so we already know in the smooth case that the Hochschild homology groups just look like differential forms. And in general, if one left Kahn extends this result, or if you just pick your favorite simplicial resolution of your ring, then it will produce for you a spectral sequence coming from homology of wedge powers of the cotangent complex converging to your Hochschild homology groups. But it's really classical that the cotangent complex, firstly, that the cotangent complex of any perfect FP algebra vanishes, and then that the cotangent complex of a quasi-regular ideal is supported in degree 1, and that all of its wedge powers are supported only in the degree corresponding to the wedgeness. So in this spectral sequence, you've only got things sitting in even degree. And there's no, in fact, there's no arrows in the spectral sequence.
Is it sensible to, forget about HP0 and just whenever you can define the developed, the divided power envelope, and then you form this this total complex of this co-simplicial complex. Is that does it make sense to do that?
Well, that's exactly what turns out to be happening here. I mean, all of these HP zeros will just be the divided power envelopes.
Yeah, but if you just if you like whenever sort of in the most general case, whenever you can define the divided power ring, and you don't start with HP.
Yeah, you could forget about the HP business. You could just start with divided power envelopes and say, let's totalize a check construction coming from divided power envelopes. And that's where this general theory of derived de Rham cohomology will kick in and tell you that the result looks like the de Rham complex. That's essentially what we have to appeal to at the very end.
Okay, and is there a comparison of this with the crystalline cohomology? Because
well, that's what we'll see. Okay, at the moment, everything, well, this is great advertisement for the talk tomorrow or the day after, is that using this type of theory, we could never produce crystalline cohomology. I mean, all of these constructions, if I input an FP algebra, they give me some complex of FP vector spaces. So some other construction has to be modified in such a way that I can input an FP algebra and output some complex of ZP modules. And that's exactly what topological cyclic homology will do for us.
Maybe one more question. No, it needs recording.
So my question is, so you have discussed over FP algebra, so can you just discuss the entire process over perfectoid fields? Does it just carry over to perfectoid, or that's upcoming?
It more or less carries over. I could replace FP, so as I said a moment ago, I could certainly replace it by any perfect field without any change, but more generally, I could replace it by any perfectoid ring without any substantial change to the arguments that I just explained.
All right, if there are any more further questions, maybe we can take them during the break. So let's thank Matthew again.